as a chart, there's no need for ones here, v and psi, then u cross v is a subset of m cross n, right? And we can build chi Cartesian product with psi that would act on, like, say, p comma q as chi of p Cartesian. Well, I could do commas here if you like. Psi of q, right? And that will be an element of our m plus n, supposing that the dimension of m is m and the dimension of n is n. The dimension of a manifold is the dimension for which the coordinate charts land in, all right?
Here the dimension is 2.
Right, so what's going on here is I'm taking the Cartesian product of the one-dimensional circle with the one-dimensional line, and I get a two-dimensional manifold, which of course is the right circular cylinder without end, right? And I can't let it have an end at the moment because I don't know, I'm not defining manifold with boundary. So to be careful, I kind of have to let my manifolds be kind of boring and go on and on and on forever. Of course, once you're talking about integration, you don't want to do this. You want your manifolds to be compact so that they're closed and bounded, and integration is a more sensible discussion there. But yeah, I'm just here, I'm recollecting, oh, my notation's better at the bottom of page 221. I actually put a chi sub m and a chi sub n on it, and I say that you can build the coordinate chart on the product manifold. This is just the product of the coordinate charts of the manifolds being producted. But this is an incredible way of building new examples from old, right? Because you can just start Cartesian producting manifolds together and get all kinds of interesting stuff. Like on my Calc 3 quiz, I did this. I asked them to find the volume of, this is a problem I gave on Calc 3. I said find the 5 volume of, and really it's the 5 volume of the set x, y, z, t, w, such that x squared plus y squared less than or equal to r squared, and z squared plus t squared plus w squared less than or equal to a squared. See that example, what it is this manifold, actually. And it is exactly the manifold, what it is, what this thing is it's the circle, right, of radius r, Cartesian product with this, with the ball. It's not even the circle, that's a disk of radius r, I should say. And the ball of radius a. So it's actually a 5-dimensional manifold inside R5. And you can calculate its volume. It's just the product of the area of the disk and the and the volume of the ball. And you can prove that by introducing coordinates that do polar coordinates for x and y and spherical coordinates for z, t, w. When you calculate the Jacobian, like we introduce in Calculus 3, you get a 5x5 matrix, but it's blocks. It's the 2x2 polar Jacobian, the 3x3 spherical Jacobian, but you know how to calculate both of them, and that's why it produces the area times the volume. That actually was in my, I actually put it as a bonus question on Calc 3 quiz this semester. I had a couple students get it. Well, one got it, one was on the way to getting it. Now, I should mention, we have another example, example 7, which is Tn, T sub n is equal to S1, Cartesian product S1, Cartesian product of that, Cartesian product S1, n-fold times. Howdy, howdy. Class time. Which class? Algebra? All right. Don't be mean to him. Oh man, I gotta grade my 121 test. Yeah. Let's see here. How are we on time? We're almost done. So Tn, this is also known as the N torus. The N torus is the Cartesian product of a circle n-fold times. All right? It is an n-dimensional manifold. So the 1 torus is a circle. The 2 torus is actually what I usually think of as a torus, right? But we know how to build a coordinate chart on that using example 5, because example 5 is S1. That is S1. M equals to S1 is example 5 from today. All right? So, yeah. And that brings us to our discussion of what we mean by a function being smooth. I guess I should do that for today. That's where we'll stop. Okay. So, if we talk about a function from one manifold to another, what does it mean to say such a function smooth? Well, I'm going to erase this business here if that's okay. Okay.
S1, of course, S1 is just a circle with a circle.
Right. But, yeah, I know. Geometrically, it's hard to visualize that. So usually we think about the one radius being much bigger than the other so you can kind of see it. But topologically, there's nothing stopping us from doing this. Although understand that this is most naturally embedded in R2n, right? Because you need a copy of R2 for each circle in the natural way. There is a diffeomorphism, I think, from the geometric torus in R3 to the 2 torus. But I'm scared to say more. I'm scared to say much more than that at the moment. All right. I think things could be said, and I'm afraid that I would say them wrong. So I will abstain from saying more about that at the moment. All right, I'm trying hard to abstain. So let me go on. So if we've got a manifold M, right? And you've got a function to a manifold N, what does it mean to say it's smooth? To say that that function is smooth, what that means is that its local coordinate representatives are smooth. So, in other words, if I have some chart domain U, and if I've got some chart domain V over here, and U maybe is by chi, and V maybe is by, I don't know, let's say eta, then we need that the mapping down here, which would be given by what? Like this, right? So that would be, the last shall be first, eta, composed with F, composed with chi inverse. Now, listen, I am getting tired of the etas and the chi's. This time will soon come when instead of writing that, I just write eta equals to y and chi equals to x, because I'd like to use x and y as charts on a manifold. And in that notation, of course, we're just looking at, y composed with f composed with x inverse. That's the mapping. So that would be a mapping from where to where? Well, that'd be mapping from Rm to Rn. If I'm sticking with my notation of m is m is m dimensional as in mommy, and n is n dimensional as in nenu nenu. which is a reference to a TV show no one's watched, but anyway. Not even I've not even really watched Mork and Mindy, truth be told. So for f to be smooth, we need that this is a smooth map down here, and smooth in the sense of advanced calculus. See? Meaning that you can calculate the Jacobian, and like it's full of partial derivatives which are continuously differentiable to all orders. C infinity, right. So this needs to be a C infinity map. Now, of course, we're really going to only insist that it be C infinity where? In the appropriate place, right? In as much as you look at, the question is which part of U. We're only looking at the part of U. So like maybe f of U looks like this, right? F of U looks like that, right? It doesn't have to be V. You see, it doesn't have to be V. But in as much as this calculation is concerned, we're really only interested in the part that maps to V. And so maybe there's just part of U which actually mapped to V. So that's the part, that's the part down here that we have to worry about. The part of the U which maps to the V, that's the place where we have to consider the smoothness of this, right? And then so to say that f is a smooth map from M to N is to say that every possible local coordinate representative of f is smooth. So if you've got a circle, you got to check all 4 charts in our current system, right? Now there's a theorem though. Well, there's some theorems that make that nicer. Like if you suppose you had like an atlas where there was a subatlas of that, which the subatlas covered the whole manifold, right? If you checked smoothness on the subatlas, that automatically implies smoothness on the larger atlas, which it's contained in. Because that automatically comes because of the transition functions. So if you have more than one chart at play, you can play games with composing the charts to get the smoothness of this to extrapolate to the smoothness of other local coordinate representatives which are touching on the same points. This can be proved. So that's pretty nice. If you can check it on an atlas which is sufficient to cover the manifold, then you've got the smoothness that you need. Now the other thing to talk about is oftentimes we talk about functions that are real valued. So in the case of a real valued function, this is easier because the case of a real valued function, right, if you've got f is like a mapping from M to the reals, right? And then in this case you have you have N is equal to the reals. So our default for that is just to take eta to be the identity map. And so this simplifies in that context to just the question, is f composed with, chi inverse as a mapping from Rm to R smooth. All right. So for a real valued map, we don't have to mess with all of these, But if you actually think about what this means, this means that there's component functions of that map, and you're going to have to look at all the different component functions, check smoothness for each component functions. If your n is a 5-dimensional space, you've got 5 component functions to worry about with respect to the domain variables. If n is a 2-dimensional space, you've got 2 component functions to worry about with respect to the smoothness of the domain variables. But if you're just looking at a real valued function from your manifold, then it suffices to check this to get smoothness of the map. Okay, so this is important because next time we're going to talk about vectors as derivations. In order to make sense of that, vectors as derivations, what is a derivation? A derivation is a linear map which obeys the Leibniz rule. A linear map of what? It's a linear map of functions which are smooth at the point. So if you want to talk about a particular point on the manifold, you talk about functions which are defined near the point. A derivation is going to be basically like a derivative on functions at that point. So in order for those derivatives to be sensible, we want to look at smooth functions. And so this is kind of the backdrop, not this so much, but more this is the backdrop for like the discussion of derivations next time. Oh, that's it for today. So,
Started talking about derivations in the introduction to manifolds group in the yellow one.
uh-huh. Oh, good, good.
So why do we only care about this section of the range of f that intersects 8?
Oh, because that's all I can care about. Because it's just not proper to even ask the question what eta does. Like if f is mapping to someplace outside the domain of eta, I can't take eta of it. You know, so it's, yeah. But to make that precise is a pain. Because I gotta look at the inverse image of the chart in the codomain and blah.
Because the function we really care about is the mapping from n to Rn.
Right. Yeah, ultimately.
Not the, which
Yeah.
is
Yeah, so like at the end of the day, it's all advanced calculus, right? Like it's all calculus on our end. Like manifold theory is, in a nutshell, a system of thievery, a system of how to lift calculus from our end to the curve space through the coordinate maps is the idea, as we shall see.